Get started. We're going to be discussing sequences and series today. So a sequence is just a list of numbers that follows a pattern. So the example here is 2, 4, 6, 8, and 10. Pattern there. It's pretty obvious. You're adding 2 every time. And this is a finite sequence because it contains 5 terms, and 5 is a finite number. But we also have infinite sequences that continue on forever, and then they use a dot 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 to show that it just continues going and going. So a series is basically adding all the terms of the sequence. So if our sequence was 2, 4, 6, 8, and 10. Well, the series version of that would be adding 2, 4, 6, 8, and 10, which is 30. So the first, most basic type of sequence is called an arithmetic sequence. And an arithmetic sequence is where the difference between 2 consecutive terms is constant. So some examples here, we have 1 and 2, 2 to 3, 3 to 4. The difference here is always 1. Difference here for the second one is always 2. The distance for the last one is always -1. So when each when the difference between each consecutive number is a constant, then we have an arithmetic sequence. Look at this first example here. The sequence 4, x1, x2, x3, x4, and 18 is an arithmetic sequence. What is the value of x3? Well, we know in an arithmetic sequence, we're going to be adding, let's say, a common difference here every time. So let's say we have d here, and then we add another d to get to x2. We add another d to get to x3, another one to get to x4, another one to get to x5, which is 18. So then this becomes 4 plus 5d is equal to 18. And then we can solve for d here. Oops, 5d. 2.8. So now they ask for x3. So when we look here, we have to add this d 1, 2, 3 times. So if we want to find the value of x3, we're going to take the first number, and then we're going to add 3d, which is 3 times 14 over 5, which gives us 4 plus 42 over 5, which is 4 plus 8.4, and that gives us our answer of 12.4. So hopefully this intuitively makes a little bit of sense. And so we can actually derive a formula for the nth term, which is, it's also pretty intuitive, but it's good to have it written out in stone here. So if we have a first term of an arithmetic sequence A, let's say value and term here. So this is the first term is going to have A as a value. The second term is going to have A plus D. The third term is going to have A plus 2D, and so on until the nth term will have A plus n minus 1 D as its value. And A will be the first term, D is the common difference, and N is the number of terms. Oops, the number of terms. So yeah. So let's look at what we have here. Consider the arithmetic sequence 1, 4, 7, 10, 13. What is the 15th term? So we set our variables. The first term is 1. Then the common difference here, we're adding 3. So then our D is 3 here. So then the 15th term, we'll have n equals 15. Our formula is going to be A plus n minus 1 times D, which is 1 plus 15 minus 1 times 3. 1 plus 14 times 3. It's a really ugly one. 14 times 3. That gives us 43. And you'd probably still be able to figure out to do 1 plus 14 times 3, even if you don't know the formula. So as long as you understand it, there's really no need to memorize it. Here's a little more complex example. So in the infinite arithmetic sequence, A1, A2, A3, ... we have the 8th term is 2001. If the common difference D is an integer, find the minimum value of D such that A17, the 17th term of the sequence is more than 10,000. So let's write it here. We have A8 is equal to 2001, and A17 is going to be greater than 10,000 here. Oops, another 0. So when you're going from the 8th term to the 17th term, how many steps are we taking here? Well, that's just going to be 17 minus 8, which is equal to 9. So if this makes sense, basically we take 1 step from the 8th term to go to the 9th, 2 steps to get to the 10th, and etc. until from the 8th to get to the 17th, we're going to have to take 9 steps upwards, and each step is going to be our common difference. So in these 9 steps, how much is it going up? Well, it's going up 10,000 minus 2001, which is 7,999. Basically, we want to go up at least 7,999 within 9 steps. So we can just do division here and say that 7,999 over 9 is equal to 888 and 7/9, which is that's what this is. So it says that the common difference D is an integer, however, and this isn't an integer. And then as for the minimum value of D, so that this is greater than 10,000. So the greatest integer, or the closest integer to this that satisfies, would just be 889, and that is our answer. And because 888 would be less than this, so we wouldn't reach 10,000, but 889 is more than our answer here, so then the 17th term will be more than 10,000. Okay. Are there any questions about this? Any clarifications? Okay, so let's move on. So when consecutive terms are in an arithmetic sequence are added, it's called an arithmetic series, as is with every series or every sequence to series. So let's look at this here. We have 1 plus 2 plus 3 plus 4 plus 99 plus 100. So one way to look at this is we can pair the first number with the last number. Then we see that we get 101 here. If we pair this one to this one, we get again, 101. And basically every time we pair here, 3 would be with 97. Oops, not 97, with 98. And then that would be 101. So we have a bunch of these 101s. And how many 101s do we have? Well, we have exactly half of as many terms as we had total, right? Because we're forming pairs here. So then we'd have 50 101s because we had 100 terms. And we can pair each two of them to form a 101. And like the exact one in the middle would be, of course, 50 and 50. So then we have 50 times 101, which is equal to 5,050. Another way to look at this is we can find the average of all of these terms. And the average is also known as the arithmetic mean. So then the average of this set would be the first number plus the last number divided by 2. And then that'd be 101 divided by 2, which is 50.5. And then we count how many terms there are. There's 100 because it goes from 1 to 100. Then we get our answer again of 50, 50. So the strategy of finding the average here is really the same thing as this pair strategy up here, except we're dividing by 2 to get the average. So from here, we can actually derive the formula for an arithmetic series. So to find this formula, what we're going to do is do the same thing we did earlier. We have the number of terms times the average term, the average value, I should say, average value. And to find the average value, it's the first term minus the last term divided by 2. So well, let's express this algebraically. So the number of terms is going to be n. And then you multiply by the first term, a, plus the last term, which remember we had a formula earlier to find the nth term. So it's going to be a times n minus 1 times d, oops, a plus n minus 1 times d. So that's the first term plus the last term. And then we divide this by 2. So this whole thing over here, this is the average, or we want to call it the arithmetic mean. So then let's simplify this. We have n, let's take the 2 out and put it over here. And then we have 2a plus dn minus d. And well, if you rewrite this, we can just write it as our equation over there. So we have a n, and then we have a 2a, and then they didn't factor out the d, which is probably a better way to do it. So n minus 1 times d. And that's where this formula here for the arithmetic series sum comes from. So I actually have never memorized this because intuitively it just makes sense to find the first term plus the last term divided by 2 and then multiply by n. So as long as you understand this process, I mean multiply the first term and last term added divided by 2 by n. So as long as you understand the process here, there's really no need to memorize any equations. But let's do an example here for the sake of it. So the sum of the first 9 terms of an arithmetic sequence is 72. What is the 5th term of the sequence? Well, so we have n equals 9 here. The common difference is unknown. They don't tell us. And then, but we have the total sum. That's right. A sigma symbol, your sum is equal to 72. And they want the 5th term of the sequence. So if we write this out, what we get is a plus, well, a plus 8d. The 8 comes from the 9 minus 1 there, over 2 times the number of terms, 9 is equal to 72. So in case you want to review where this is coming from, a is the first term, the ninth term will be a plus 8d. Then you add the first and the last term, and then you divide by 2 to get the average. Then we multiply by 9. I should write this a little higher. We multiply by 9 to get the sum of all of the 9 terms, and then it's equal to 72. Well, let's simplify what we have here. We have 2a plus 8d over 2, and then there's a times 9, so then we can divide both sides of the equation by 9 to get rid of it. So then we have 72 divided by 9 is 8. So then we have, well, that's really ugly d. I'm going to write it again. 2a plus 8d over 2 is equal to 8. So now they want the fifth term. And then the fifth term would be a plus 4d. So with this information, we can't really find a or d individually. But if you notice that what we have here is actually going to give us a plus 4d equals 8. And that matches what we want here for our fifth term. So our answer to this problem is 8. Oops. Okay, so in this example, a lot of times your first instinct to solve problems will be to find either D or A first, but in this case, it wasn't possible. They never gave us enough information to actually solve for the common difference or to solve for the first number. But if we paid attention to what they asked for, which was the fifth term of the sequence, we realized that although it'd be nice for us to find A or D, the value we're really looking for is A plus 4D, and we're able to obtain that from the information they did give us. So the lesson here is to always pay attention to what the question is asking for. Let's do another example. The sum of the first 5 terms in the arithmetic sequence is 70, and the sum of the first 10 terms of this arithmetic series is 210. So what is the first term of this series? And the first term is, we call it A. So let's try approaching this with the formula again. So we have the sum of the first 5 terms. So that would be A plus 4D over 2 times 5. It's equal to 70. And the sum of the first 10 terms, so A plus the 10th term, A plus 9D over 2 times 10. It's equal to 210. And what is A? So this time, they're not asking for something special, they're just asking for the first number. So let's just try to approach this analytically. We have 2a plus 4d over 2 times 5 is equal to 70. Let's simplify this. A plus 2d is equal to 14. And then let's stop there and look at our other equation. We have 2a plus 9d over 2 times 10 is equal to 210. Divide both sides by 5. And we get 2a plus 9d. Why did I write 29? 9d is equal to 42. So we go from here to there. So then we have these two and these two equations. So now we can use a system of equations to solve this. So let's say if a plus 2d is 14, a is going to be 14 minus 2d. So we substitute it in here. We have 14 minus 2d. So we're substituting this value of A into there, plus 9D is equal to 42. And then we get, I'll write it in a different color to make it more clear. We have 28 minus 4D plus 9D is equal to 42. So then we have 28 plus 5D is 42. And then 5D is equal to 42 minus 28. That's going to give us 14. And then D will be 14 over 5, which is 2.8. And they wanted the first term of the sequence, so it probably would have been smarter to solve for A instead of solving for D, but you know, we can just substitute it back in. It's not a big deal. A is equal to 14 minus 2D as we wrote here. So then we have 14 minus 2 times 2.8, and that gives us 14 minus 5.6, which should be 8.4. And that is our answer. So we actually covered system of equations on day 1 this week. So just rehashing that the stuff you learn will come up all the time, especially the algebra stuff. So it's good to have a good grip on it. Okay, there are some special cases here that you should be able to memorize. So the first one would be the sum of the first n positive integers. So that's equal to n times n plus 1 divided by 2. So for example, we did 1 plus 2 plus 3 plus 100 earlier, and we came out to 50/50. Well, if we use this formula, we'd get the same result. So we do n times n plus 1 divided by 2, which is 50/50. These two, the sum of the first n squares, so this would be like 1 plus 4 plus 9 plus 25 plus 16 plus n squared is actually equal to this. And I'd say this formula is a little less important, but it does come up when you're taking pre-calculus and calculus, when you're doing like Riemann sums and stuff like that. But yeah, this also comes up. And so does the sum of the cubes. And the sum of the cubes equation, which would be like 1 plus 8 plus 27 plus 64, and so on. This would be equal to this equation here. And you'll notice that this equation is actually the square of the positive integers one. But again, these two are not too important. This one you should definitely know by heart. Here's an interesting one. The sum of the first n odd numbers is n squared. Like, so what I'm saying is, let's say the sum of the first 5 odd numbers, 1 plus 3 plus 5 plus 7 plus 9. When you add this up, you're going to get 25. And you notice that this is actually 5 squared. That's pretty interesting. So if we have the sum of like the first 10 odd numbers, 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13, 15, 17, 19. Well, since these are 10 odd numbers, it's just going to be 10 squared and it's 100. So this is just a cool little trick to add up the first n odd numbers. You just square n. I thought that was pretty interesting. So a geometric sequence is a sequence which consecutive terms have a common ratio. So here we're multiplying by 2 in between each of these terms. So their common ratio here is 2. So then the formula for the nth term of a geometric sequence will be a times r to the power of n minus 1. The reason for this is if we have a first term a, let's make another table here. Term value, second term, third term, fourth term. We're gonna have a for the first one, a times r for the second one, a times r squared for the third one, a times r cubed for the fourth one, and for the nth one, we're gonna have a times r to the n minus 1. It's kind of similar to what we did for the arithmetic sequence, but instead of adding a common term, we're multiplying by a common term for a geometric sequence. Oops. So here's our example here. Let x, y, and z be real numbers such that 3x, y, z, 27 is a geometric sequence. So find all possible values of x, y, and z. Oops. So then here we're multiplying by r, we're multiplying by r, we're multiplying by r, and then we're multiplying by r again. So what we're going to have is 3 times r to the fourth power is equal to 27. And then when you solve for this, you're going to get r to the fourth is equal to 9, r squared is equal to 3. So r is going to be plus or minus root 3. So then our possible values of x, y, and z are going to be, let's write it out here. So we have 3, let's assume positive. So this is for positive root 3. Then we're going to have r as negative root 3. This is the sign for positive or negative, plus or minus. So we have 3 root 3, 9 root 3, 27. Or we can have the negative version, which is going to give us this. So our combinations of x, y, and z will be 3 root 3, 9 root 3, or the same thing, but with negatives on the 3 root 3 and the negative 9 root 3. Okay. So earlier we talked about the arithmetic mean, where it was like we had a numbers, and let's say we added all of them up and we divided them by a, or n numbers, I should say. So the geometric mean is kind of the exact same thing, but we use multiplication everywhere. And instead of dividing by the total amount of numbers, we take the nth root. So for example, if we wanted the geometric mean, let's make a set here. So let's say we have the numbers 1, 4, 16, 20. These are just random numbers. So the arithmetic mean, which is the average, as you guys probably have learned it, is going to be 1 plus 4 plus 6 plus 20 over 4. So the geometric mean is going to be 1 times 4 times 6 times 20. Then instead of dividing by 4, you're going to take the fourth root. So just like how an arithmetic mean, once you find it and you multiply by the total, we got the total. With the geometric mean, once you can take this and take this to the nth power to get the regular product of all the numbers. So it's like a similar concept as the arithmetic mean, but we're replacing all addition with multiplication. So let's look here. Our geometric sequence starts 16, negative 24, 36, negative 54. What is the common ratio? So to find the common ratio, we can just divide this term by this term. Do negative 24 divided by 16, which is going to be negative 6 over 4, negative 3 over 2. And then if you want to check this, we can multiply each of these subsequent terms by this ratio and see if it matches. And yes, we get 36 here. Then 36 times negative 3 over 2 is going to give us negative 54. So basically, geometric series, instead of common difference, is a common ratio. So to find this common ratio, instead of subtracting these terms, we can divide these terms. So geometric series, of course, is just the sum of the terms in the geometric sequence. And there's also an equation for this, and it's a little less intuitive than the equation for an arithmetic sum. So this is the equation here. So you have the sum of the numbers is the first term, a, times 1 minus r, where r is the ratio, to the nth power, where n is the number of terms, all divided by 1 over r. So this probably doesn't immediately, the way how we derive this isn't probably immediately clear, but let me see if I can try to explain the derivation. So let's say this sum is equal to a would be the first term, then a times r, second term, a times r squared, dot, 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 plus a times r to the n minus 1. So this equation is going to have n terms. So what we do here is, let's actually multiply this entire thing here. Let's multiply this by r. Then we get SR, where S is the sum, of course, is equal to AR plus AR squared plus AR cubed plus AR to the nth. And this time it's not n minus 1, because everything, you notice the powers of r here are all one more than the one above, because well, we're multiplying by r. So from here, we can actually notice that we have these corresponding terms here, and there'd be one here too. And our second to last term over here would be a to the r minus 1. I'll write it. And then this term here would correspond to this term here. So when we have these corresponding terms, let's try subtracting them. So if we do, let's do rs minus s. So what we're going to get is, well, all these terms in the middle here, all of these terms are going to cancel out with these terms. So then all we're left with is AR to the nth minus A. So does that make sense? Because these terms from A times R to A to the power A times R to the n plus 1, all of these terms that I circled are contained in both of these values here, S and S times R. So when we subtract S from SR, they're going to cancel out. Oops, why am I drawing? So then now we have this here. And then we can rewrite this as, oops, factor to S. We can S times R minus 1 is equal to A. Let's factor to A here. Rn minus. And then once we solve this for S, that's going to give us S is equal to A times Rn minus 1 over R minus 1. And we can reorder this, multiply top and bottom by -1. So instead of Rn minus 1, we can have 1 minus Rn. And on the bottom, we'll have 1 minus R. And this is where our equation for a geometric series comes from. So did everyone kind of follow that derivation process here? Are there any parts that I should review? All right, so looks like we're good there. So clear that. And then we'll start solving some problems. Evaluate 1 plus 2 plus 4 plus 8 dot 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 plus 1024. So our equation, once again, is a 1 minus r to the n over 1 minus r. So this is going to give us a, the first term is 1. The ratio between terms is 2. And how many terms are there? Well, this is 2 to the 0th, 2 to the 1st, 2 to the 2nd. This is 2 to the 10th. So we're going to have 0 to 10th powers here. So we have 11 terms here. So n is 11. Then we have a times 1 minus, I should substitute the values. I should say 1 times 1 minus r, which is 2 to the 11th power over 1 minus. This is going to give us negative 2047 over negative 1, which is going to give us 2047. As an application of this formula. All right, so here is where it gets a little more interesting, because unlike arithmetic sequences, we can find the values of infinite geometric series. Because, so if we have an infinite arithmetic sequence, and when we add it up, we find a series value, I should say, you're always going to get either infinity or negative infinity. Because, well, the numbers will either keep getting larger or they're going to keep getting smaller. But when we have geometric series, what happens is that these terms will actually, like this value here, we have 1/2 plus 1/4 plus 1/8. This will actually approach a value. This is not going to go, will not go to infinity. No. So let's think about how we can solve this problem. So we have 1/4, 1/2, 1/4, 1/8, 1/16, whatever. So when in doubt, as is the rule of thumb whenever you're doing math problems, give this variable. So let's call this n, or let's call it s, I should say. Well, let's try something. Let's take 2s here. 2s will be 2 times, well, 1/4 plus 1/4, or 1/2 plus 1/4, 1/8, blah, blah, blah. And this will come out to 1 plus 2/4 plus 2/8, dot, 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 which is going to give us 1 plus 1/2 plus 1/4, dot, 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 dot. So then we notice something very interesting here. So these terms here, from 1/2 all the way to 1/2 to like infinity, or to the infinitieth term, not to infinity. This is actually equal to our original s here. Notice that, right? These terms here, they match these terms. So what we're actually saying here is 2s is equal to 1 plus s. And now this tells us that s is equal to 1. So that's pretty interesting. When we have 1/2, 1/4 plus 1/8, then we add half of whatever was before, and we do this for infinitely as long. This total sum will actually approach 1, which might not be intuitive, because usually infinite terms, you'd think that the sum would be infinity. But no, that's not the case with geometric sums sometimes, because as these values get so small and so small, they become almost negligible. So when the sum doesn't approach an infinity, we say that it converges. So the key to knowing if a geometric series converges is to seeing if the absolute value of the ratio is less than 1. So if the absolute value of the ratio is less than 1, which is like what we had before, 1/2, 1/4, this ratio was 1/2, and 1/2 is less than 1. So if it's less than 1, then the series will converge, which means basically just means it approaches finite value. But if the ratio is, or the absolute value of the ratio is greater than 1, or even if it's equal to 1, then it's going to diverge, which basically means approaches an infinity. So it could be negative infinity or positive infinity. So we can look at this. If we say r equals 2, well, then our numbers will be 1, 2, 4, 8, dot, dot, dot. And obviously, if this goes on infinitely, we're going to have infinitely large terms here. I don't know. With all these terms, we're going to do infinity, go to infinity here. So here, we cannot find an infinite geometric sum if the ratio is more than 1 or less than -1, since there's an absolute value. So there's a formula to find the sum of an infinite geometric series. So the formula is a over 1 minus r. And then it's actually based off of the previous formula we derived earlier. So this was a regular geometric. Let's say, remember for infinite geometric series, r, absolute value of r must be less than or less than 1, because we want the terms to get smaller. Terms get smaller as you get to like the infinite term. Because if the terms get bigger, well, and it goes on infinitely as long, we're not going to reach a finite answer there. So if the terms get smaller, then we can find the value of the infinite geometric. This is actually an important topic in calculus too. So let's look at what we have here. So the formula said a over 1 minus r to the nth over 1 minus r. So let's look at this term here. Well, if our r is less than 1, let's give it like a value like 1/3, and n was our number of the number of items in this series, right? So this is an infinite series. So we're going to have infinity here. Well, anything that satisfies the absolute value of it, if it's less than 1, and we take this to the infinite power, well, this is going to get less and less and less and less. And if you do this infinitely long, it's basically going to be 0. So then what we have is 1 minus 0 here, which is just 1. So this entire term here, when you're looking at an infinite series, it becomes 1. So that's why this equation can be simplified to a over 1 minus r for an infinite geometric series. Look at this problem here. We have 3 plus 1/3, 3 plus 1 plus 1/3 plus 1. A is the first term is 3, r is the ratio. We're dividing by 3 here, so the ratio is 1/3. Our formula is very simple. We just go a over 1 minus r, 3 divided by 2/3, which is going to give us 4.5. And if we wanted to check this, we can use the strategy we did from earlier with the 1/2 one. Let's call this s again. So we have 3s is equal to 9 plus 3 plus 1 plus 1/3. dot dot dot, which is the same as 9 plus s, because this term is just an s. So we have 3s equals 9 plus s, 2s equal to 9, s is equal to 4.5. So this way, this strategy here is a little more, I think it makes a little more sense. This one's more abstract, it's just a formula. But why did I write 4.9 here? 4.5. So yeah, so either way you can solve a problem like this. It's not too important. So let's look at this. We have 1.1 plus 1.1 squared plus 1.1 cubed, dot, dot, dot. So our first term is 1.1. Our ratio here, well, it's 1.1. So then we can do a over 1 minus r to get 1.1 over negative 0.1, which is going to give us negative 11, right? And then immediately you look at this and you say, wait, this doesn't make any sense because these are all positive numbers. And you can't add up a bunch of positive numbers and get this negative number, can we? The answer is no, you can't. And the problem here is that this ratio here is 1.1. And remember that you can only find an infinite geometric series if the absolute value of r is less than 1. And here, 1.1 obviously is not less than 1. If you think about this, these values would keep getting bigger and bigger slowly. They become 10% more every time. And after you do this infinite amount of times, you're going to have infinitely large numbers. And when we add those, we're not going to reach a value of anything that's finite. So make sure to check the ratios. Okay, so I had a question sent to me. Does it matter if you use the formula of the arithmetic sequence formula or the other one to solve any problem, even if it is different? The other one, well, I'm not sure which one you mean when you say the other one, but hopefully when you're solving these problems, it should be clear whether you have an arithmetic or a geometric series, and you can choose which formula you're doing. So if it's a constant ratio, approach it geometrically, and if it's a constant difference, then it's arithmetically. Yeah, a geometric series and arithmetic sequences, they're very different because one of them you're adding a constant term, and then and then the other one you're multiplying by a constant term. You get like this or something. So these are very different, and you can't apply one formula to the other one. So let's look at this infinite geometric series. Evaluate the sum of 4 minus 8/3 plus 69th minus blah, blah, blah. So first thing we do is find the ratio. And to find the ratio, we can just divide the two terms. So we do negative 8/3 divided by 4. That gives us negative 2/3. And we have to check here to make sure that the absolute value of r is less than 1, of course, because it's an infinite series. So absolute value of negative 2/3 is going to be 2/3, and that is indeed less than 1. So we're good to go here. So we just plug this into our formula, a over 1 minus r equal to 4 over 1 minus negative 2/3. And this gives us 4 over 5/3, I believe, yeah. And then that's going to give us 12/5, which is 2.4. And this is a lot less intuitive. So this, you basically have to know the trick here because you have a positive term, a negative term here, positive term here, negative term here. And without knowing this formula, or at least knowing the strategy of approaching this problem, very hard for you to intuitively think of what it's going to be. So let's do some series, but with algebra now. So find the value of x for which 1 plus x squared plus x cubed dot 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 infinitely long equals 4. Well, this is a geometric series here because we're multiplying by x every time. So this is an infinite one too. So we can use our infinite theorem, which is a over 1 minus r, just to reiterate. 1 over 1 minus x. This is equal to 4. So then this equation becomes, how to say it? Oops, this equation becomes 4 minus 4x is equal to 1. Negative 4x equals negative 3. X is equal to 3/4. I think there's one more of these. Find the value of x that satisfy x equals 1 minus x plus x squared minus x cubed plus x fourth. So when you see these, when you see these alternating signs here, see these signs are going minus plus minus plus, this tells you that the ratio is going to be negative. So the ratio here is we're multiplying by negative x every time. So then we have 1, a over 1 minus r, I'll write it again, over 1 minus r. We said r is negative x, so it's 1 minus negative x, and we say just 1 plus x is equal to x. And then we write this as x plus x squared is equal to 1. X squared plus x minus, x, what am I saying? X squared plus x minus 1 equals 0. And again, this is a quadratic equation, which I haven't gone over. So I probably shouldn't put this in here either. But when you do solve it, which if you've taken algebra, you know how, but if you haven't, I apologize, I didn't go over it, and I should not put this problem here, but you're going to get x is equal to 1 plus or minus root 5 over 2. Yeah. So the earlier example, I put one in like this too. Keep forgetting. You guys are a bit younger, sorry. So now there's this interesting trick here with recurring decimals. What is 0.127272727 expressed as a fraction? Well, you guys might have seen this written more like with this bar on top. So that's basically what this is. Well, we can actually break this down with geometric series and try to follow along here as I go through this process. So we have this number here. So let's split this into smaller fractions. Let's say this is equal to 0.1 plus 0.02 plus 0.007 plus 0.0002 dot, 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 dot. And if you express these as fractions, you'll get this. You'll get 1/10 plus 2/100ths, or I'll write 2 over 10 squared, plus 7 over 10 cubed, plus 2 over 10 to the 4th, plus 7 over 10 to the 5th, dot, 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 dot. Yeah, it goes on. Well, you'll notice here that we can actually split this into two geometric series here. These terms and these terms each form a geometric series. And if this isn't clear, I'll write them out. We're going to have 2 over 10 squared plus 2 over, all right, 10 to the 4th plus 2 over 10 to the 6th, dot, 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 infinitely for these. And then for these, we're going to have 7 over 10 cubed plus 7 over 10 to the 5th plus 7 over 10 to the 7th, da 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 da. So yeah, so that goes on. Well, for these, well, we know how to solve these actually, because these are just infinite geometric series. So remember our formula again, it's a over 1 minus r. So then we're going to have basically a here is 2 over 100 over 1 minus the ratio here is going to be, we're dividing by 100 each time. And similarly for this one, we're going to have a, which is 7 over 1000 over 1 minus r, and of course we're dividing by 100 every time here, so it's going to be 1 over 100 again. And then let's make this look a little nicer maybe. This is going to be 0.02 over 0.99. This is going to be 0.007 over 0.9. So let's, so what we have is we're adding all of these terms. Add these two, we're going to get 0.027 over 0.9. Of course, that looks kind of bad, so we're going to rewrite this as 27 over 990. So we're multiplying by 1,000. And then don't forget, we have a 1/10 term over here. So then our sum here, this sum here, is going to be 1/10 plus, so box that off, 1/10 plus 27 over 990, which is going to give us 99 plus 27 over 990, which is going to be 126 over 990. And you'll notice both of these are divisible by 9. And they're also divisible by 18. And then when you simplify this, you get 7 over 55. And that is our answer for this question. So does anyone want me to review any part of that? Well, okay. So clear then? And so that was kind of a long and tedious process, and it turns out we don't actually have to do any of it because there's a trick, but it's good to understand the process, so that's why I did it. So the trick is, let's say we have a digit a over 9, well, expressed as a decimal, that's going to be 0.8, so on. And then if we have two digits, AB over 99, that's going to be 0.AB repeating. And I should probably just write it here. You guys might see it like this instead. And then if there's ABC over 999, then it's going to be 0.ABC. So that's the trick here. And the proof for this is basically it's the same process as what I did above, except we do a generalized case instead of a specific case. But yeah, it's the same idea. So let's look at our problem from up there. Well, we have 0.127272727. So that's going to be, well, 0.127. So we have this decimal in this place here, and then these repeating ones. So it's a little annoying that we can't immediately apply this. But if we simply multiply this by 10, we'd get 1 point repeating 27. And of course, now we can apply this trick and say this is just 1 and 27 over 99. And if we write that as an improper fraction, that's going to give us 126 over 99. But of course, we have to remember that we multiplied by 10 to get rid of this 1 here. So we're going to have to divide by 10 again. So then we're going to have this instead. And of course, this simplifies to 7/55, as we said. So yeah, this is just a cool trick with repeating decimals. If you ever see them, just think that every spot that's repeating, give it a 9, and then yeah. So let's look at this one. What fraction is 0.5 to equal to? Okay, so of course we have this one in the way here, so we're going to multiply by 10 to get rid of it. So we're going to have times 10 multiplied by 10 here. We're going to have 5.22222. And then this is going to be 5 2/9, which is just going to be 47/9. But of course, we multiply by 10 here. So then our final answer, we're going to have to divide by 10 again to get 47/90. And yeah, so that's why, 1/3 is equal to, 0.33333 ... So the reason for that is because, well, 1/3 is the same as 3/9, and that follows the rule that we've been setting here. And you guys might have heard that 0.9 repeating is equal to 1. Well, that's true. If this goes on infinitely long, this is not going to approach 1. This is going to be 1. And it's kind of a hard concept to understand. But if you think of it in terms of this rule here, it's going to be 9/9, and that's obviously 1. But yeah. Let's do 2 more examples here. So we have repeating decimals 27, or 0.727272. So that's just literally going to be 72/99. And then that's going to simplify to what, 8/11. And then for this one, we multiply by 100 here to get rid of this term in the front. So let's say 63.36. Repeating instead, that's going to be 63 and 36/99. And then that's just 63 and 4/11. And then we multiply this into an improper fraction. So let's do 11 times 63 plus 4 gives us 697/11. And of course, we multiplied by 100. So we're going to have to divide by 100. So our answer here is going to be this juicy fraction is going to come out to this. Yeah, so that's pretty cool. So another strategy when you're solving long equations, or I should say long series and stuff, is called telescoping. And basically, when you have this telescoping, you're going to have terms that cancel out, and then the entire series will collapse like a telescope. So let's look at this example here. 1,000 minus 999 plus 998. Oops, 1,000 minus 998 plus 998 minus 996, and so on. You guys can read it. So you can think of this as, this is a 2. This is also a 2. This is also a 2. And then this is also a 2. So basically, you're going to do 2 times the number of 2s. But there's actually an even easier way, which some of you guys probably realize, because we don't even want to bother counting the number of 2s here. We can literally notice that these 2 terms are going to cancel out. These 2 terms are going to cancel out. Every term in the middle here is going to cancel out, because these parentheses literally mean nothing. They're just there to confuse us and make us fall into this trap of counting the number of 2s. No. You have a minus 998 plus 998 minus 996 plus 996, etc. So we can literally remove everything here in the middle. And then we get 1,000 minus 332 is equal to 668. That is our answer. And then if we were to count, that would mean there were 334 2s. But yeah, we don't even have to worry about that. So yeah, so whenever you see something long like this, always look for terms that are going to cancel out, and you can telescope the problem, so to say. And for this one, it was pretty clear that what would it be, but sometimes it's a lot harder to see. This one, so you have this gnarly product here. 3 over 1 times 4/3 times 4/2 times 5/3 times 6/4 all the way up to 40 over 30. So we think, okay, where do we have terms that will cancel out? Well, these terms, these two 3s, these two 4s, there's going to be a 5 in here, etc. Until we get to, I'll write down a few terms here, times 37 times 38, then there's the times 39 there. So these terms are going to cancel out, these terms are also going to cancel out. So everything here from here and everything from here, well, they're the same, and then they get canceled out, and then this problem becomes 39 times 40 over 2. And then this is just going to be 20 times 39, which is 780. So in this example and the last example, you can see pretty clearly how terms would cancel out. But now let's look at this problem here. This is a very complex telescoping question. So they want you to evaluate the sum of 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, 1 over 4 times 5, dot, 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 plus 1 over 99 times 100. Well, of course, they definitely don't want you to manually do this with fractions and add them up. No, they'll never ask you to do something that tedious. So let's analyze this. Is this a geometric sequence? Well, not quite, because the bottom here, we're not multiplying by a constant ratio. The ratio is changing. So here is where a strategy that comes up that you guys might already know, but it's very simple. It's called testing. So we're going to plug values in here and see if we notice anything special. So let's start with the first two terms here. So if we have 1 over 1 times 2 plus 1 over 2 times 3, well, that's just 1/2 plus 1/6 is, that's going to give us 2/3. Okay, so then let's try something else. Let's try the next one. 1/2 plus 2/3 plus, not 2/3, 2 times 3 plus 1 over the next term, 3 times 4. Well, this is just going to be 2/3 plus 1/12. And then if you add that up, you're going to get 9/12, which is 3/4. Okay, so let's do one more. So from 1/2 to 2 times 3, 2 times 4, 3 times 4, 4 times 5 here. So what we have here is 3/4 plus 1/20. And if you do this, you're going to get 16 over 20. 4/5 here. So hopefully you guys should be realizing a pattern. We have a 2/3, 3/4, 4/5. Logically speaking, just like disregard for any math, just from a pattern recognition. If this is like an IQ test or something, we'd say that the next one is 5/6, then 6/7, etc. Because that's the pattern we're noticing. And then eventually, if we were to generalize this, we would say 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. This is going to give us, if we go to, let's say, the n, let's say we go to the n over, sorry, we go to the 1 over n times n plus 1 term. Well, the answer to this is going to be n over n plus 1. And this is a pattern we noticed from doing all the smaller examples. Here, we had n equals 2, n equals 3, n equals 4. N equals 2 gave us 2/3, n equals 3 gave us 3/4, n equals 4 gave us 4/5. So logically, we're saying if n equals n, then we're going to get n over n plus 1. And we haven't done any real math here. We've literally just noticed a pattern. And by this pattern, it turns out that, well, this pattern is true. So when we're looking for this here, from all these terms, when you add them up, what you're going to get, well, you're going to get 90. Well, you're going to get 99 over 99 plus 1, which is going to give us 99 over 100. And this is our answer. And turns out this is the correct answer. And I know this might be very unsatisfactory to just notice a pattern and assume it's true, but trust me, 99% of the time, it is going to happen in competition math, at least. But we could actually prove this. We could prove this is true algebraically, because what we had were fractions of the form of. We're trying to prove that this was true. So then all of these fractions were of the form 1 over k times k plus 1. Then if you do this thing called partial fraction decomposition, basically splitting up a fraction that has 2 terms in its denominator. You guys will probably learn it later, either in algebra or calculus. Well, then basically, once you do this process, which I'm not going to show here because I don't think anyone really cares to see it, but what you get is that this is equal to 1 over k minus 1 over k plus 1. And then, of course, when you combine these terms, you end up matching some stuff here. And then when you simplify this, it will actually prove to you that this equation is true. And yeah, so this process here, in competition math, you probably won't have time to prove it, but it's always good to be able to prove it. But if you don't know how to prove it, or you can't prove it, but if you notice a pattern, stick to your guts and follow the pattern. So pattern searching is very useful. Let's go over a few more. Let's review our problem solving strategies. So make sure you look at what the question is asking. So if it asks you for something that isn't the value of a variable that you're solving for, there's probably an easier path than to finding that value. Because sometimes they'll make you do it, but rarely do they ever give you extra calculations at the end for no reason. Like, remember we had the problem earlier that gave you the 9th term and we wanted to find the 5th term? Well, we could have, if we tried to find the first term and the common difference, we couldn't have solved the problem. But paying attention to what they're asking for allowed us to find the easier path to solve that question. And some series can be evaluated by combining 2 smaller series. And this is actually, we saw this in the example where I proved the recurring decimals one. We split the recurring decimal into 2 separate series. And yeah. And if you're stuck, test cases and search for patterns, even if you cannot prove them. This is not, of course, it's not mathematically, how to say, it's not mathematically rigorous or correct, but it just, in my experience, I've found that this is a super useful strategy. Okay, so let's get to the final questions, final set of problems for today. Let's look at this one. Compute 1 minus 2 plus 3 minus 4 plus 5, dot, 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 dot. So, easiest way to look here is we have a -1 here, a -1 here, a -1 here. So every pair is -1. How many pairs do you have? Well, if there's 100 terms, you're going to have 100 minus 2, which is, or 100 divided by 2, which is 50 pairs. And we have 50 times -1, going to be -50. Very simple. pattern searching and telescoping come up everywhere. So here's a bit harder one. So let the C be the sum of the first positive even integers. So C is equal to 1 plus 2 plus 4 plus 6 plus 8, blah, 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 plus 200, because there's 100. Okay, and then let D be the sum of the first 100 positive odd integers. So it's going to be 1 plus 3 plus 5 plus 7 dot, 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 plus 199. So they want C plus D divided by C minus D. Well, we know some tricks here to make these a lot easier. So for the first one, let's say, instead of writing it like this, let's write it like, let's factor it to, right? It says 1 plus 2 plus 3 plus 4, da, 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 plus 100. And of course, we know how to solve this. This is going to be 100 times 101 over 2. And we multiply this by 2, and it's going to give us 1010. C is 1010. Because of course, you want to always remember. If you remember nothing else from this lesson, just remember this formula. From 1 to n will be n times n plus 1 over 2. It comes up everywhere. Okay, and then on the bottom here, we have the sum of the odd integers. And remember the super cool trick that the sum of the first n odd integers is just n squared. So these are the first 100 odd integers. This is just going to be 100 squared, which is 10,000. And now we can solve for C plus D over C minus D. And that's going to be 1010 plus 10,000 over 1010 minus 10,000. Then it will give us 11010 over negative 8,990, I believe. My arithmetic math is not great. Yeah, so then this comes out to negative 1101 over 899. And let me check if that can be simplified. No, it cannot. So this is our answer to this question. So earlier I said always pay attention to the answer to see if there's a shorter way to do it. But in this question, we just solved it rigorously. We just found C, we found D, using special tricks, of course. Then we just solved it from there. So we didn't apply that rule there, but it's still good to make sure to check what they're looking for. So Eric arranges the counting numbers, which is 1, 2, 3, 4, 5, and so on, in a triangle by writing 1 at the apex, 2 and 3 on the second row, and then 4, 5, and 6 on the third row, and so on. What are the sum of the first and last integers on the 17th row? Well, let me make this problem a little easier to at least visualize. This is the first row, the second row, the third row, whatever. So you notice that in the third row, we'll have used 1 plus 2 plus 3 terms. And by the fourth row, it's going to be 7, 8, 9, 10. We'll have used, well, this plus 4 terms. So by the nth row, we'll have used 1 plus 2 dot 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 plus n terms. And of course, this should look familiar. It's the formula I just said pops up everywhere, and here it is. It pops up immediately. I promise I did not plan that. So by the 16th row, we'll already have gone through 1 plus, make this more clear, 1 plus 2 plus 3 dot 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 plus 16, which is going to be 16 times 17 over 2, which comes out to 136. So So that means that through the 16th row, I'm just going to skip 16th row, we're going to have 136 as our last number. Then for the 17th row, that means we're starting at 137, and then we're going to end up, if 137 is the first term of the row, then the last term of the row will be 137 plus 16 to give us 153, because there are 17 terms in this row. So then we want the sum of the first and last integers. That's going to be 137 plus 153, which gives us 290. Again, re-emphasizing this very important, very useful. So consider the non-decreasing sequence of positive integers 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, 4, 5, 5, 5, 5, 4, 4, 4, 4, 5, 5, 5, 5, 5, in which the nth positive integer appears n times. So what is the 1993rd term? So solve this, you'll notice that, again, this is popping up again. We'll have 1, this is for the number of terms. We'll have 1, 1, 2, 2s, 3, 3s, 4, 4s, dot, 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 dot. So then, basically what they're saying here is they want 1993rd term. So let's think of it this way. We want 1 plus 2 plus 3, dot, 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 dot. And then eventually this is going to be somewhere around 1993. So we want to see in what range does 1993 fall. So let's go to plus n. So let's rewrite this. Let's say n times n plus 1 over 2. And then the problem we want to solve here is equal to 1990. So I said it's around. So here we just want an estimation. So let's estimate here. N times n plus 1 is going to be equal to 1993 times 2. And that's going to give us what, 3986. Now, so we want something that's around this area. So remember this nth term, it appears n times. So we don't need to know like the exact number, because at this point we're going to have that number so many times. We just need a general area. So if we want, let's just take an estimate here. Let's take the square root of, n and n plus 1 are going to be pretty close. So we can treat them as the same number. Since we're being broad here, we're kind of doing a guess and check here, which is usually a no-no, but in certain scenarios, it's perfectly a fine strategy. So the square root of this number comes out to like 63.13. So we're going to be around this 63 area. So let's start with something less than 63. Let's start with 62. So basically what we're saying is 1 plus 2 plus 2 plus 3 plus, actually we're not even adding them. We're saying 1, 2, 2, 3, 3, 3, dot, dot, dot. Then we're going to have 62, 62, 62. Have this 62 times. So how many terms have we used up here? Well, that's just going to be 1 plus 2 plus 3, blah, 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 plus 62. And then, so that's going to be 62 times 63 divided by 2, which comes out to 1953. So the first 1953 terms are encompassed by this series here. So we want the 1993rd term. So you'll notice that after all these 62s, we're going to have 63s, and we're going to have 63 of them. And of course, 1993, 1993 is well within the range of 63 terms after 1953 because 1950, I'm so messy. I apologize for the messiness, but 1953 plus 63. So all the way up to the 2016th term. So from the 1954th term to the 2016th term, these are all going to be 63. So then the 1993rd term is going to be 63, and that is our answer. So yeah, so in this problem, we used a bit of guessing and checking strategy because this 1993 here, we couldn't write an explicit equation for it because the numbers repeat so many times, but basically we found the general area and then we did guessing and checking near that correct area. And that's how we found the answer. I think I've see a few. This example requires a little bit of algebra knowledge. I'll just skip it. I'll just do this one for the last one for today. So we have 1 over 2 plus 2 over 4 plus 3 over 8, blah, 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 etc. This question, well, you look at it, you might think, oh, it's a geometric sequence because the denominator is divided by 2 every time. Nope. You see the top is also increasing, so it's not a geometric sequence. And then it's not an arithmetic sequence either because, well, the top's increasing, like this is arithmetic because you're adding the same thing, but the bottom is geometric. So this is a little bit annoying to deal with. So as is, anytime you have something in math, as I said before, and you don't know how to do it, assign it a variable name. So let's call this, I'll clear this out. Let's call this entire thing S. Call this S. So I'll get rid of those 2 circles too. Oh, I went too far. Okay, let's call this S. So you'll notice that when you write these terms out, it's going to look like 1/2 plus 2/4 plus 3/8 plus 4/16 here. So well, these 2 terms you notice are the same. So this basically indicates to you that maybe we can find a very similar sequence here and do some work on it. So what do we know how to solve? Remember this sequence? Well, this is just the ratio here. This is just a geometric infinite series. I keep saying sequence, but it's a series. This is an infinite geometric series, which we earlier proved is equal to 1. So what if we do this interesting thing here? Let's take S. Let's do S minus 1. And the reason for this is we see some terms here that are matching. And specifically, I'm referring to this 1/2. So S minus 1 will be, well, we have S, that was 1/2 plus 2/4 plus 3/8 plus 4/16, minus 1/2 plus 1/4 plus 1/8, because this here is equal to 1. Well, we'll notice that we'll have some terms here that cancel out. We're going to have instead S minus 1 is equal to, I'll change colors to make this more clear to see. Eliminate the 1/2. We have 2/4 minus 1/4. So this gives us 1/4. Then we have, I'll keep changing colors here, 3/8 and 1/8. So 3/8 minus 1/8, it's going to be 2/8. And then we're going to have, I'll do one more. We have 4/16 here. We'd have 1/16 here. So then we'd have plus 3/16. Well, now this will go on forever. So let's go back and look at our S here. Oops, here's our S. Well, let's try dividing this S by 2. So instead of this, you're going to have, instead of 1/2 to the first power, you have 1/2 squared plus 1/2 cubed plus 1/2 to the fourth. Oops, I forgot to increase the numerator. The numerator is increasing. Dot, dot, dot. Well, bingo. We found a pattern. This matches what we have here. And then rewriting this, we have S minus 1 equals S minus 2. I mean, S divided by 2. And then we have, well, 2S minus 2 is equal to S. S is equal to 2. Boom. That is our answer for this seemingly super difficult sum. Once we defined it, a variable, and then we found a geometric sequence we did know, and we combined them, and we found a pattern. So when you're solving these kinds of questions, pattern searching, I think it's pretty fun, and it's also a super useful skill in these kind of questions. So yeah, and that is all I have to offer for today. Well, that will conclude this Mira Loma math camp and the competition course that I made. So hopefully everyone at least learned something, and thank you to everyone for participating.
Thank you.
All right. You're welcome. And yeah, I'll post the videos to all of these up later in case you want to review them. So yeah.